This video is about quantum entanglement. Now, quantum entanglement is a phenomenon where two or more particles become linked in such a way that the state of one instantly determines the state of the other, no matter the distance. Here's your basic setup. You create a pair of particles, say photons or electrons, in such a way that their quantum states are correlated. For example, their spins, polarizations, momenta, stuff like that are all tied together. Now, once they're entangled, you want to separate them. Put one somewhere like New York and somewhere like London. Now, when you measure particle A, immediately the state of particle B is determined, even if it's light years away. Now, I want you to imagine there are two electrons that are entangled in terms of spin. The total spin of the pair must add up to 0, no matter what. So, if one is measured to spin up, the other must be spin down. But before measurement, both exist in a superposition. So that's up and down simultaneously. And here's where you get a recurring theme with quantum mechanics. You see, almost everything is in a superposition in such interpretations. With Schrodinger's cat, you can look at that in one of my other videos. We see that the cat is both in a state of dead and alive until observed. The same is similar with the electrons. We don't know, in this example with spin, if one is spin up or spin down until we measure, so they are both up and down at the same time. So, the moment you measure electron A, electron B's spin is instantly fixed, even across any distance. Now, the weird part is, this effect is instantaneous. It apparently seems to happen faster than light, which breaks Einstein's relativity rules, at least on the surface. Now here's the catch. You can't use this to send information faster than light, since no actual signals are transmitted. It's correlation, not communication. Now, here's why it matters. Entanglement shows quantum states are not local. They aren't confined to one place or another. Reality may not be made of separate, independent parts, the way classical physics assumed. And measurements don't just reveal reality, it can define it. Here's a little argument between Einstein and Bohr. So, Einstein hated this particular idea. He had argued that entanglement showed quantum mechanics must be incomplete, proposing that there must be hidden variables determining outcomes. Now, Niels Bohr and some others said, nope, this is just how quantum reality works. And this debate lasted decades. Now, Bell's theorem, 1964. Physicist John Bell had devised a way to test whether hidden variables were real or if quantum mechanics was correct. Now, experiments in the 1970s show entanglement is actually real. Quantum predictions match experiments, and hidden variables, at least the local kind, don't actually work. So, entanglement isn't a theory. It's been proven again and again and again. So, here are the applications of quantum entanglement. So, this spooky phenomenon is now being harnessed for real technology, such as quantum teleportation. This is the transferring quantum states across distance. Quantum cryptography, unbreakable communication systems. Even though we know entanglement has nothing to do with communication, but correlation. Quantum computing. Entanglement is a key resource for performing calculations far beyond classical computers. Now, here are the different interpretations. The Copenhagen interpretation. The particles exist in superposition until measured The measurement collapses both states simultaneously. The many worlds interpretation says there's no collapse whatsoever. Each measurement branches the universe. In one universe, you see spin up, and the other spin down. The pilot wave interpretation tells us the particle have always been in that defined state, but a hidden pilot wave connects them across that space. Now, the relational QM says that the properties only exist in relation to the observer making the measurement.